actually our third deep learning meetup, and we're focusing on image classification. We have a great talk today and a great speaker, Ronnie Hore. He's the founder of Learn.ai. Learn.ai is a startup that helps promote deep learning papers and make deep learning papers accessible to data scientists. I'd also like to thank MINST for hosting the event. Thanks to Sam and Yuval for hosting this event. MINST is a deep learning platform to help data scientists manage their resources, experiments, and data on AWS, Azure, and on-premise. Also, my last thing is also like to thank Samsung Next for contributing to this event. So, without further ado, I'll introduce Ronnie.
Hi everyone.
Okay.
Thanks for inviting me. I'm Ronnie. First time I'm giving a talk in English. I'm originally from Israel, so help me out here. Ask questions. Let me know if I'm talking too fast. Feel free. Anyway, this is just a cool video I saw online yesterday. There's no sound, so it just shows SGD, stochastic gradient descent, and how it works. It's just a cool visualization, and it's the basic of all deep learning. You can look it up later and post the slides. So we're going to talk about MNIST, Kuzushiji, and ResNet. How many of you heard about the MNIST? Oh, that's a good start. Good. Okay. Kuzushiji? I guess. No one? That's not fair. It's a friend of mine. And ResNet? Pretty good. Okay. We'll talk about all of them. Let me know if you have any questions. So a bit about myself, because Yuval asked. So I'm Rani. I'm originally from Israel. As I said, I'm a researcher and a developer for over 10 years. I also founded a startup. As part of it, we created Learn.ai. And I couldn't find any profile picture, so I'm an amateur photographer, and that's just the one to find. So what's on our agenda? Learn.ai. We talked about that already. So what's Learn.ai? The idea is to make deep learning papers more accessible to people. We know that most people, including myself, aren't experts, but they want to stay informed. They want to read, they want to know what's going on in the world in deep learning. And what we are trying to do is to make these papers more accessible to them by summarizing complicated papers. And it's hard to read papers. Even after I read basically reviewers, conferences that read everything and they know exactly by heart the citations and the references, and it's easy for them. For me, I had to just jump back and forth between papers just to understand what's going on. And what we are trying to do is take this complicated topic and just let people give them a better way to read these papers. 5 to 10 minutes later. So that's enough for me and Learn.ai. Let's talk about MNIST. MNIST is an acronym to National Institute for Standards and Technology, something like that. And the M is modified, it's the name of the data set. It was created around like 21 years ago by Jan LeCun and some of his friends. Jan LeCun is like the director of AI at Facebook. He's a famous guy. And they collected 70,000 images of digits, like that. These 9 digits. with the idea to build an algorithm that can somehow recognize these handwritten numbers to pass checks and have like improve their systems and instead of like just someone reading the checks manually. And today this is basically the hello world of machine learning. When you want to start doing like anything that's related to deep learning and image recognition, that's how you start. You take these images, this data set, and that's how you start. So let's say you have 70,000 images of digits. Like, meaning it means like 7,000 images per digit. How would you classify them? What's like the first thing that comes to mind? Something? OK, so deep learning is an option, of course. But before we had deep learning, we did a, yeah, SVM is a great option. The first thing they tried is just k-nearest neighbors. It's like in one sentence, k-nearest neighbors means that you find the closest. You have a training data, then you want to take a new image, a new digit, and you want to classify it. You find like the most similar image by just like calculate the distance between pixels, and that's how you classify the digits. What you see here is a visualization of MNIST on two-dimensional visualization with TS&E. It's a great algorithm for visualization invented by Jeffrey Hinton. If you've heard about PCA, it's kind of similar, but in my opinion, better. And what you can see here, for example, all the ones, like all the digits of 1 are kind of in the same cluster, same for 4, 7, and so on. So you can see that even like with one nearest neighbor, it's going to work pretty well. And as you can see here, they tried the k nearest neighbors, and they reached like this is like the, as you can see, SVM is on the list here. They tried the k nearest neighbors, and of course, convolutional neural network. What is convolutional neural network? In just an overview, and we'll dig into it later. You basically take the input, and you multiply like small parts of the image by learned values. At the end, the goal is to create some kind of a representation of the image that can be later on used using another layer to classify the numbers. And we'll talk about some of these things later. I'm assuming that you know what CNN is, but just feel free to ask. OK, so they started with KNN, moved to SVM, CNN, and basically today, problem solved. No one is actually using MNIST anymore because it's too easy. And what's interesting is that ImageNet, which is like the most famous data set for image recognition today, which is much bigger than the MNIST, is going through the same process. Like, ImageNet became actually almost too easy. And that's a problem that researchers are facing today. So far, we talked about MNIST. Let's talk about Kuzushiji. So what you see here is a keyboard, a Japanese keyboard. But apparently, this is just part of the keyboard. Google built this keyboard. I don't know why. Look at this button at Google Brain Tokyo. The Japanese script is different than what we used to from what we know. In English, it's easy. You have like 26, 24. How many? 26? Yeah, somewhere there.
I think 24 is easy.
Could be. Sorry. So it's easy. You have just 26 letters, and you represent a word with a bunch of letters. In Japanese, they have a different system. They have two systems. One logographic system,
For example, kanji is one of them, in which a symbol represents a word or a phrase. So we have just one symbol that means like the entire, even like more than one word. And there are like over 10,000 symbols. And they are using like 3,000, like most people know like around like 2,000 to 3,000. But still, like, what happens if there's a word that you don't know how to write? What do? So they have another system, the syllabary system, which is like kind of like ours, not exactly the same, but kind of like ours. Like each symbol represents a phonetic word, a phonetic letter. Like our alphabet, they have like 49 symbols. Some actually like 46 are in use, but they have 49. You can see them here. And they use both systems, like even like at the same time. Because sometimes you just don't know how to spell a word in kanji, so you move to hiragana, which is like the syllabary system. And now we get to Kuzushiji, which is a cursive script. This lovely thing that I can't read. Maybe do we have anyone here who can? Probably not. Like they're just like probably a few dozen people in the world today that are able to read Kuzushiji. Like it's not easy to read in general, and someone on the internet said like the more common a character is, the worse it looks. Which is not a good. It's like my handwriting, basically. Like my wife here just complains all the time that she can't read my handwriting. So what's the problem with Kuzushiji, and why do we care about it? Like, what does it matter? It's just like an old language. Who cares? So until 1900, there was no standardization. Like Kuzushiji was basically a lot of variations of letters and symbols, and you can see here, for example, this is just one symbol, and it has like 1, 2, 3, 4, like 8 different representations. It depends on like the area in Japan, and depends on like the time and so on. And it was like in use for like over 1,000 years. So most people can't read it, and even the ones that can, it depends on the exact variation. And in Japan, there are 3 million documents and books that almost no one can read, and there's an institute for open data in Japan that is trying to kind of like revive this language, but at least somehow preserve these documents, because a lot of Japan's history is in these documents. And there are dictionaries. You can go like, use a dictionary and just translate letter by letter and translate like 3 million documents, but you'll probably it's gonna take a while. So what's the solution? Luckily, we have machine learning for the rescue, and you can use that to restore this like almost lost language and restore these documents. And that's what they're trying to do. And you can go to their website and you can look it up, and they're like publishing the updates on the project and what's going on and so on. And the way they approach this problem is by releasing data. That's the key for machine learning in general. Just they released 3 datasets that anyone can use and help them restore this language. So the first one, they decided to create a kind of like Kuzushiji MNIST, which is like exactly like MNIST, but with Japanese letters. The difference is that instead of like just let's take 0 as a digit, there's basically one version of 0. For them, in this, even just with 10 characters, they have like dozens of variations for each character. So the challenge is a bit bigger than just MNIST. And then they did the same thing with all 49 letters of hiragana. I'll just go back. Hiragana is the syllabary system. These letters. This is it's still in use, hiragana, but not with the cursive script, with new scripts. So they created another data set with one difference. The classes aren't balanced, meaning like for one letter you have, let's say, 5,000 samples, and for another letter you have like 1,000. So it means that the algorithms are a bit different, and you have to take into account like how you train your models. And the last one is the Kuzushiji kanji, which has over 3,800 symbols. A much harder challenge, and like what makes it even like harder is that for some symbols they have basically 1, 2, or 3 samples. That's all. And I don't think any deep learning model can learn from just 3 samples. So it explains why it's harder. And what they did as part of this research is to just provide like a few baselines. And they started by running like 4 nearest neighbors, and they compared it to MNIST, Kuzushiji MNIST, and 49. They still haven't ran it on the Kuzushiji kanji. We lost it. That's it?
Thanks for coming, everyone.
Ah, it was great.
I'll get you a charge.
Oh, it's not my.
The computer has power.
Yeah.
Oh, the computer's on?
Yeah. Let me see.
Computer's dying.
Probably.
Okay.
Let's try.
Can you spell it? Yeah. That's
Oh, okay.
All right. Thanks for coming back.
So we talked about k-nearest neighbors, and then they ran, again, SVM. It's better, but not much better. And of course, the next step is going deeper to deep learning. And they ran their version of ResNet 18. We'll talk about ResNet in a second. And I read about the paper and the dataset and decided to summarize it because I found it interesting. And as a side project, I decided to run an ensemble of ResNet and VGG, which is another version of deep learning, another model, deep learning model. And somehow I got like 98.9, which is better than theirs. Like, in my opinion, is there any difference between like 98.83 and 98.9? Not really. Like, it was just a fun project, and it's there. It's on the GitHub, which is nice, but it doesn't really matter. Like, there is no difference for most algorithms, except if you work for Google, and like any like small like 0.01% like means a lot of money. For us, it doesn't matter. It doesn't like move the needle. It doesn't. But it's still like it's a good experience, and I'm going to talk about ResNet and a bit about ensembles, just to give you like an overview of what's going on there, like behind the hood, underneath the hood. So what's ResNet? It's an acronym for residual network. And why do we need that? The biggest problem with deep learning models, one of the problems, I won't say the biggest, is the vanishing gradients problem. It basically means that if we have a deep network, when you're trying to train a network that is just too deep, we fail to train the earlier layers, like the first layers. And the reason is that when you use backpropagation in deep learning, apparently the data isn't like, and the information that you're trying to learn isn't being passed from you run the network, you take the input and you pass it through the network, and when you're trying to backpropagate back to train and to update the weights of the network, it doesn't matter what's the result here. It doesn't affect the earlier layers, and that's a problem. Yeah. Yeah. You mean like the gradient is the vanishing gradients problem, or in general ResNet? So I think you can find. Yeah, you can find. Yeah, this is from the paper itself, and there's a nice blog post on ResNet and like the problem of yeah.
Can you share the slide after?
Yeah, definitely.
Was this run on LSTM as well?
You're right. Like the problem LSTM is
Was this taken in LSTM as well to the vanishing gradient problem, or it was just ran only on ResNet?
it's yeah.
Yeah, repeat the question.
Oh.
I was asking if this was also taken in LSTM network as well.
The problem?
Yeah.
So
was done a comparison, or it was just ran only on ResNet?
Okay. The question is if this problem does this problem exist also in LSTM, in RNN, like recurrent neural networks, and it exists in any network basically. LSTM helps fixing it.
Was taken because this problem LSTM is supposed to work better compared to
You're right. LSTM is a long-term short memory network, and the idea in LSTM is that you pass the knowledge between the layers to help the network like remember or forget things. There are other problems with LSTM. One of them is it's really slow on images. But for CNN, for convolutional neural networks, we can't use LSTM, and we're looking for another way. And which is, you'll see in a second, it's kind of like the idea of LSTM that you pass like the knowledge to the deeper levels. And what you can see here is that they tried more. Sorry about it. They tried like networks with like 56 layers compared to 20 layers. And you can see that actually the error is like going up instead of going down. And the authors of the paper said like, it doesn't make any sense. If I add more layers, it shouldn't like affect and make the model worse, just better. So that's the problem they're trying to fix, and that's how Microsoft invented ResNet. So if you need to remember just one thing from ResNet this is just this line. That's all. That's the idea of ResNet. Everything else is basically kind of the same as any other convolutional neural network. ResNet is there. That's all. So simple, so genius. That's what's nice about it. And what they're trying to do is to help backpropagation by passing the data through all the layers, and I'll talk about the layers in a second, and then taking the result of the convolutional batch norm ReLU, convolution batch norm, take all of these and add the original inputs. So it means that you just add the residual to the original input. So you pass the image all the time through the network. And what it does, it helps the network when you propagate back, like the information isn't getting lost. Because think about it, if you don't have this part, like when you pass it through a lot of, this is just one block of ResNet, and the actual ResNet is, let's see if I have it here, is basically ResNet 18 means that you have like around like 6 blocks of that, something like that. So the information isn't being passed through the network, and once you add this nice addition, then it solves the problem, which is amazing. So simple. Let's talk about like what's going on here in general. So let's see. I think I have something here hidden. Sorry about it. So what's convolution? We talked about it at the beginning, but let's go over it again. You take a bunch of pixels, and you multiply them by a filter, a bunch of weights, and you get one result. And then you go over the image one by one until you get the new values. They kind of like, they're related to the original image, but they represent like something completely different. And you can see, for example, if you look at the layers in VGG, you can see that the network actually learns like lines and shapes and aspects of the image. For example, like in deeper layers, you can learn like faces, and in earlier layers, the network learn like just like lines and shapes, simple shapes. So this is convolutional layer, and another part that we have there is ReLU, which like sounds like out of this world, but it's basically that's ReLU. All you do is take the values that are below 0 and you make them like 0, and that's all. That's ReLU, like rectified linear unit. Sounds like complicated. So we talked about that one. Batch norm. Batch norm is a batch normalization. We still don't really understand why we need batch norm, and it's an open discussion. Batch norm means that you take the data, the input, you take a batch of like images, and you normalize the values. Meaning instead of you shift everything to be around 0 with a variance of 1, and you do that with a learned layer, just like 2 parameters to learn the, yes. Go ahead.
There was no max pooling. Was it a max pooling or an average pooling? Was there pooling? I don't see.
Oh, it's not here. You can see it. There's max pooling here before, and then there are like a few here that just with strides. And at the end, we have average pooling. By the way, average and max pooling, if you think about it, just one word about max pooling and average pooling. It means that you take a bunch, like a group, for example, 3 on 3 pixels, and you take the average or the max of them and set that as a new value. And when you think about it, it doesn't make any sense because you lose a lot of data. You have different pixels, different values, and you just like combine them. And that's what Jeffrey Hinton is trying to solve. He's one of the founders of AI. He's trying to solve for like over 10 years with the capsule networks. He's trying to fix. He said like we have to find a better way to reduce the dimensionality of the data instead of just like taking the max value. He's still trying. I guess it's hard. So so back to batch norm. We just normalize data. There is an open discussion about it if we need it or not, and there are dozens of papers about it and why. One of the problems with deep learning that some things we just don't know how to explain and like why it works and like, what to do with it, and that's a problem because it means that we are moving from like a scientific discussion to just like I don't know, like gut feelings, and that's not a good way to handle like math. So this is the batch norm, and we just do it over and over again, and we add more layers. And what's nice about ResNet is because of this identity addition, we can jump from 19 layers, 22 to 152, which is like a big improvement. And what you can see here is the top 5 accuracy of different algorithms on ImageNet. And you have like AlexNet here, VGG, GoogleNet, and ResNet. And there are new ones since then, like Inception 4 and so on, and it's basically endless. So this is like ResNet. Any questions? Here? This is the accuracy on ImageNet. The top one, like, it's the, oh, sorry, it's the error rate. Sorry about it. It's like the opposite. So it means like that that 3 out of 100 images are classified incorrectly. Okay, just for comparison, like most of us are somewhere here. So it's pretty good. So we talked about convolution. We talked about value. Let's talk about the code a bit. I'm not going to go over like every line here, but just to give you an idea of like, it's pretty simple to implement ResNet today. It sounds like quite complicated, but they wrapped a lot of things for us, and like smart people mainly at Google and Google and Facebook. Google with TensorFlow, Facebook with PyTorch, like the two main frameworks for deep learning. They wrapped a lot of things for us, and to implement batch norm, all you need to do is just call batch norm. So you can see it's almost like line, like each line is just like, that's all you need to implement ResNet. And you can see this is a basic block of ResNet. And there are two parts. There's the initialization of the like layers, and then the forward pass. So you call, once you initialize the network, you call the forward pass, and you pass the actual data through the network, and you do that in training, and then you pass it back with backpropagation to learn the weights, and you pass it just forward afterwards in production when you actually want to classify images or anything like that, when you want to classify Kuzushiji letters. So we have one block here. You can see here, that's all ResNet does. That's pretty amazing. Like, when you think about like, that's all they actually added. Like, they wrote a paper about it, and like, it's an amazing invention, but it's just that. OK, so we have a ResNet block. Now we have a ResNet. Let's build the entire ResNet network. And you can see here, this is like the architecture of the network. What we have here is like, it's the first convolution layer. They add like 7 on 7. That's like, it's pretty common use. There are some explanations that you want like a bigger convolution to get like bigger parts of the image and reduce the dimensionality quickly. And then they use like max pool. And all you see here is just like these like blocks. They're just adding more and more layers. And if you want to move from, this is ResNet 18. If you want to move to ResNet 152, all you do is just add more blocks. Just more and more blocks, and you combine them just to make sure that you take the right dimensions. And at the end, and the last thing you add is a fully connected layer, like the basic deep learning layer, just with the idea that you want to transform the end result of the network to the output that you're looking for. For example, if you want to classify 10 digits, then the output is going to be 10 here. So you move, if I'll go back for a second, so you saw that at the beginning. So this is the input, this is the digit. And you pass through convolution layers. And at the end, you move from the end result of the network to, this is the fully connected layer. And you can see where the name is coming from. Like, it's fully connected. And at the end result, you get like 10 outputs, one for each digit. If you have 1,000 classes of images, then the output here is going to be 1,000. And the result here, the meaning of it is like the probability that this digit is actually the image that we just ran through the network. That's the entire ResNet. Let's see. Yeah. Any questions? Yeah. About what?
For the dropout.
Mm-hmm.
So usually during the training time, we find dropout at the subsequent layers.
Mm-hmm.
The dropout ratio keeps on increasing as we go deeper and deeper.
I'm sorry, but can you speak a bit louder?
So the dropout ratio keeps on increasing as we go deeper into the network.
Mm-hmm.
And once the model is trained, after that during the inference time,
Mm-hmm.
So I want to understand how the connections are made during the test time, because if, say for example, at the fifth layer, if you are using 0.5 as a dropout, and if we are just randomly selecting few neurons to be connected, and we have learned those weights over time, how do we connect those neurons during the test time? Because we are not using dropout during the test time.
So the question is, how do you use dropout? I'll try and explain. Let's see if I've somewhat, I can. What's dropout? Let's start with it. The idea behind dropout is to prevent overfitting. So what we do is when we train the network, we randomly pick some of the neurons, some of the information, and just drop it. Just ignore it to make sure that the training data, we are not overfitting for the training data, and we're just using, so the entire network has to work even when just some parts of the network, some parts are missing. That's the idea behind dropout. And the way we do that in code is by adding dropouts here in different locations in the code. By the way, the nice way to implement it is to set the dropout ratio as a variable, and then in production, you just set the value again to 0, and then you won't drop anything. So that's just for coding purposes. The way it works is by the dropout. What we do with the dropout in order, if for example we use dropout, then we're kind of changing the network. So let's say you're doing max pool, or for example average, then you can't just use dropout and set zeros. You have to actually know that. Let's say you're trying to average 9 numbers, and then you dropped 3 of them. You can still divide the result by 9. You have to divide it by 6. So the dropout module actually does that for you. What it does is it compensates for the missing values. For example, you can take the average instead of let's say you have 9 values, and then you dropped 3 of them. Then you replace 3 of them with just the average of these values, and then you can somehow overcome this issue. Mm-hmm.
As we're not using the dropout, and all the connections will be between the 2 layers, there will be a full connection,
mm-hmm.
no dropout. In that case, assuming that those 2 layers were connected with the 0.5 dropout during the training time,
mm-hmm.
and we have the learned weight and bias value between those 2 layers for just 0.5, that is half connections,
mm-hmm.
then how do we predict the other weights and bias for the different neurons between those 2 layers in the test time?
I see. I hope I'm going to answer your question. You're not dropping the same neurons and same connections all the time. Every time you drop different connections. So in inference, you're not going to do that. You're going to use, for example, let's go back. Let's say you have all these connections. So you run you're taking a batch and you're training. Yuval, you're more than welcome to help me if you want. So let's say that.
Continue offline after the specific question.
Okay, definitely. So let's move back. So we have ResNet. I ran ResNet. I ran VGG, which is another deep learning model. And I got decent results. And then decided, okay, what can I do next? Let's see how I can just improve my model. What's the simplest thing I can do to improve my model? And they went to Ensemble. And the idea behind Ensembles is to combine multiple models. It can be 2 or 10 or as many as you want, and leverage the strength of each one, because VGG and ResNet are different, and they basically they analyze the data differently. So by combining the 2, I can maybe reach better results. Of course, I'm paying for it. And the reason I'm paying for it is that I'm training now 2 models. So before that, I trained ResNet and I trained VGG, and now I need to train both. So how do I train both? It's as simple as that. That's all you need to create an ensemble. Like, again, it sounds like complicated, but that's all you need. I created like a VGG, I created ResNet, and then I went for the simplest solution. I took the results of each. So when you run ResNet and when you run VGG, you get, for example, with the Kuzushiji MNIST 10, you get 10 values at the end, with the probability of each of the image to be related to each symbol. So you get 10 values and 10 values from VGG, and you just take the average, and that's all you need to do to create an ensemble. Another solution could be to remove the fully connected layer or remove the soft marks at the end. And so instead, you'll get, for example, I'm going back again. You'll get just, you're cutting the network here. You're getting the result from VGG. You're taking the results from ResNet. And then you combine the two and use the two. You just push both of them together to a fully connected layer and then a softmax. That's also an option. Just I went like the basic one. Yeah.
In the data processing, are those 2 architectures, they take the same input dimension?
The input is
Adding 2 architectures.
at the end of them, or
Yeah, no, of the like 224 by 224, both of them, or do you have to do any processing because the input dimension of the input vector?
So I'm giving both of them the same image. So the input is identical.
They like same architecture,
They both starts with a they both start with a 28 on 28 image.
So we have to make sure they are the same. They have, because some
No, you don't have to. No, that's fine. Like, for example, if there is, let's say if the output is different, then you can't use like my solution. If the output is, for example, 1024 and the other one is 512, then you can't use that solution. You have to remove the last fully connected layer and the softmax, and then, for example, just concatenate the 2 outputs and pass them through fully connected layer. Okay? And that's how I got to 98.9 accuracy, which is nice, but just the idea is to give you like cool ideas on what you can do with the deep learning, and just to show you that say like the monster isn't that awful. Like, it's pretty much accessible once you know what to do. And we'll talk about it in a second. So that's all I have to say about Kuzushiji, ResNet, MNIST. They're still working on it. They're still they have other challenges. For example, they need somehow to extract the digits, the symbols from the. They need to scan the documents, and they need to separate different symbols because some of them are kind of like overlapping. So they have other challenges that they are working on, but deep learning is definitely going to help and is already making an impact in restoring this language. And it's just one example out of like many. And what you can see here is like something that DeepMind released 2 days ago. They are trying to improve the wind farms and produce and to optimize the electricity that they're producing. And what they did was to predict the weather, and by that improve their wind farms by 20%. They can predict the weather in 36 hours ahead, and by that they know how many power they need and how to pass the electricity into the grid network. So just like it's just one example, and like DeepMind is doing like amazing things. They just like released like a month ago about protein, analyzing proteins and generating new proteins, and there are many other things. However, we are still far from like let's call it like artificial general intelligence and like robots that are going to take over the world. We're basically trying to train them to grasp objects at the moment. So there's a long way to go. Some other notes: don't chase state of the art as I did. It's meaningless in my opinion. Build things that actually can help people and make an impact. Use existing tools. There are great tools around. Like, for example, there's FastAI. So, like, if you want to move from, like, if you're looking for a theoretical understanding of deep learning, that's not a place in my opinion. But if you want to actually learn how to build deep learning models, then FastAI is amazing. They have an online course. They have they released a report that wraps a lot of the things for you. So that's a good start in my opinion. But it's important to understand what's under the hood. Don't just like copy and paste, because then if like things like one of the problems with deep learning is that it's not going to work when you start. When you first time you write code, it's not going to work, and it's much harder to debug compared to just normal code. So it's important to understand what's going on underneath and how you can just look at the results and like debug it like step by step. And the last thing, data. Like most of us, including myself, we're not going to invent the next algorithm, the next ResNet. We're going to take existing algorithms, and the most important thing is to make sure that we have the right data. We have enough data, we have enough sample, exactly like they did with Kuzushiji. Collect enough data, make sure your data is reliable, make sure if you have any biases that you are aware of, and that's the most important thing in my opinion in deep learning. Not the models. The models are kind of like common and anyone can use. Yeah.
How many GPUs did you use for this?
One, I trained it like for an hour on the MNIST 10. It was a bit longer on the 49. Yeah, I used it on Amazon on a P2 actually, for like an hour or so. Don't try it. Don't try it, honestly. By the way, in order to make the training of the Ensemble faster, I already trained VGG and ResNet, and I just used their weights, and I initialized the Ensemble with these weights. So I have to just add like a few more epochs, and that's all I need to train the Ensemble. It's nice. If you want to use ensembles and you've already trained other models, then use it instead of starting from scratch. So let's show you like FastAI. I think so we can. So this is the website FastAI, and they have a GitHub with a, and you can see here if you want to learn more, they have everything here. Deep learning for coders, and you can. I'm not expecting to read it right now, but you can find like they have 2 courses on deep learning, one on machine learning, like classical machine learning, which is also great. So you can start with that, and they have the repo with everything is like the lectures and a lot of like packages that you can use, which are great. Just a few more things that we're doing in Learn AI. So you can read. This is our blog, and you can read like summaries that we're on deep learning, and we're also just building some tools to help us and help others to just navigate this increasingly growing world. And for example, what you see here is I'll click one. We built an algorithm, a tool that helps us navigate between papers, and you can. What you see here is a paper, and you can see all the references of the paper. And if you double click on one of the papers, you can see all the citations and the references, and you can see the authors and the references and the citations, and just it helps you navigate between papers. You can just, we lost it again. Yeah, let's reset. Ah, never mind. That's the last one anyway. Oh. Hmm? You mean the backend, or I collected like 40,000 papers from archive.org. I think it's MongoDB. Yeah, and there's a visualization JavaScript package. That's all. I think. Any questions? Yeah.
Make sure to repeat the question.
Can't promise. Yeah. That's fine. I'll repeat the question.
We're in a small crowd.
No worries.
It's not so important, but as a newcomer into this
Mhm.
topic, so there are different kinds of models, there's AGG, ResNet,
Mhm.
and so on. As a newcomer, and if I get a data set, what should be my first approach? Do I say, okay, I take the last models and I just
You don't have to if you want. I can repeat the question. Up to you.
so do I take the last best models and then try out my evolutional neural network on that, or?
For you mean like for images?
Yes.
Yeah, you can. I won't start with like the last one. The cutting. Probably they tend to be like more complicated, and I'll try something that is like half a year old, something like that, just because you know that enough people actually used it, and you have enough information about it.
And then do you use a pre-trained?
It depends. If
Take a
when you can use pre-training, when you can use transfer learning, use it. Transfer learning means that you use like models that others already trained, and you start from them and train your model. If you can use a pre-trained model, then that's great. For example, for digits or Kuzushiji, it doesn't make any sense because ResNet was trained on images of dogs and cats.
what, for example, if I have a set of medical images, would I use a pre-trained?
What kind of medical images?
Colorectal cancer.
I have no idea. Could be. You maybe even just want to use just like the top, like the earlier layers, which I used for. Yeah.
Just the last question.
Go ahead.
When can I consider to be happy with which accuracy?
That's like the.
Repeat the question.
Something.
When.
I'll be happy already if I have 80% accuracy. So when should I stop working?
When should you stop training? There are two answers for that. One, it depends on your goal. If you're gonna tell the patient if he's gonna die or not, then 80% isn't good. That's for sure. But on the other hand, if you see that the results aren't getting better when you train more, then there's no reason to train. You need to find something else. Probably more data. That's the answer for all that. One option that you have a bug. Other option is you need more data and better data. Yeah, I can post it. Yeah, I'll add it to the show.
Do you use data augmentation techniques?
For Kuzushiji? Yeah. So the question is, did I use data augmentation? Data augmentation means that you change the input a bit in different ways. You can zoom in, zoom out, crop, and so on. And I did that. And it actually it helps because it makes the model more robust. So I tried expanding and and zooming in, zooming out a bit. And I tried. Of course, I won't mirror or flip the letters because it doesn't make any sense. But I did try to move them a bit to the sides. Any questions?
The question is about your company.
Yeah.
You basically work on the existing papers and prepare a summary and present it in a readable or maybe a more understandable format.
True.
So, if somebody wants to just like to read papers and implement them, can they contribute to the website that supposedly it's not there yet?
Yeah, definitely. If you want to write summaries,
Yes.
definitely you can just ping us and we'll publish everything. The only thing that we're doing some kind of a vetting process. What we're trying to do is to create high quality summaries. So we're going over the summaries and we're going to edit them. But you are more than welcome to send us.
Do the summaries have to be backed by experiments or can
No, definitely. Most of our summaries, for example, we published a summary on style-based guns. It's kind of getting a lot of buzz lately. So we just published the summary without any experiment. And then others actually read the summary, and if you've heard about this website that the name is This Person Does Not Exist. So the guy read the summary and decided to write, to take the model and build this website. So it's just up to you.
Yeah, it's coming to your papers. Can we search by citation just in deep learning, say computer vision, based on maximum citation papers? Because it's just so overwhelming papers, and there are ones with very high citations I probably want to look at.
So you can do it on our website. There is another website by LNAI that allows you to do that. The issue is that if you're looking for new papers, they won't have a lot of citations. So what we do, and you can use it if you want, is to use archive.learnai, and we took archive sanity. It was developed by Anvek Karpathy, and we added top Twitter or most and hype. And here you can, for example, you can see the most hyped papers from the last month on Twitter, and you can see the tweets, and you can go and see the discussions there. And this is one of the tools I'm using to find new papers. So you're more than welcome to use this website. And we're probably gonna rebuild the website and add more features. And one of the things we're planning to do is to also add a collaborative platform. So you can write notes on papers, and others can answer questions, or you can add your thoughts about it. Because currently, when I'm reading a paper, no one else can read my notes. And I'm not that smart, but there are others that their notes actually worth something. Yeah. Any other questions? Yeah.
So maybe it's a stupid question, but going on your slides, when you showed us the error, showing the vanishing gradient descent. When you showed us the graphs for the error, there was a point where the error began to be stable and then dropped down very quickly.
Let's go back.
So I would like to understand, why does that happen? I mean, when at a certain point you see that the training error starts to, at the beginning it's decreasing quite fast, but then it kind of stabilizes and then drops. There is a drop from 3 more, for example.
You mean here? Why? So it depends on the learning algorithm, but probably just as part of SGD, you're trying different areas of the space. So in order to find the global maxima, and I'm guessing that it means that you just jump to another location, which is better. And then you can see that then you get stuck again because the improvements there aren't as big. And actually, the video from the start explains it pretty well. Like you can see here.
Activating gradient.
You can see that you're starting a different path, like in different areas. So if you start in one position, then different than another. Yeah. Go ahead.
When you run a convolutional neural network,
Mm-hmm.
you get the curve over the efforts over time,
Mm-hmm.
curve of the loss function of the accuracy. What if you make this experiment several times? I tried that on a simple example, and I found out that each time I run the convolutional neural network, the curves are different. How to deal with that? Do I need to make several realizations of the run to get kind of the smooth average?
The
Question is?
Hmm?
The question is?
The question? When she runs, no, that's fine. The model, when she trains the model, every time the accuracy graph looks it's different. And the reason is that because there is like randomness in the training, and you initialize the weights differently, and therefore every time it's just.
Can we have a checkpoint and capture the checkpoint?
Yeah, definitely.
And then reload it and probably run it if
What you mean is that you can save the results during the training, and then you can get back to it later. But it's going to be different every time. But if your model is built, you build it correctly, it should converge to the same value. So it doesn't matter that the path is different. It should be the end result should be kind of the same. Not necessarily, because sometimes theoretically you can converge into a global minima. But in general, it shouldn't matter. I hope. Did I answer your question?
Comment on this. It's probably because of whenever you run a model, it initializes itself. So if you fix the seed, if it's not a random seed, then you'll get it accurate up to the last decimal place. So then it will be the same seed every time you run it, even on a different processor.
Yeah, I understand. But when you do that in a professional context,
Just use the microphone.
when you do that in a professional context, do you have to rerun?
In general, it's enough to train it once.
Yeah, it's enough to train it once.
We'll take one more question, I think, and then we can continue questions offline.
Okay. Anything else? Okay.
Right. I will just add one point then about so TensorFlow often does parallelization techniques, which also will cause some randomness because which thread that's doing what will update. But I found that actually PyTorch is more reproducible in my experience. But maybe if you do set the seeds to begin with, but your experience might vary. So
I find PyTorch much easier to use.
in that too.
Yeah.
Right,
Thank you
so-
for coming. Hope it was interesting.
Thank you for presenting.
Thank you, Yuval.
Right. Thank you, folks. Yeah, make sure to get the last pieces of pizza.